We are going to discuss about the examples first, then we will discuss Hess's law of heat summation and Born-Haber cycle. Example number 2, page number 204 of your book. Question is neutralization of 100 centimeter cube of 0.5 molar NaOH and 100 centimeter cube of 0.5 molar HCl. Both are with the same volume and same molarity. NaOH and NCl both having same volume and same molarity. They are reacting means the reaction is neutralization. When acid and base react, the neutralization reaction takes place. Salt and water is formed. Basically, in this reaction, we are going to calculate the enthalpy of water when 1 mole of water is formed. So some temperature change is also mentioned here. Specific heat of water is that is represented as S is 4.2 joule per Kelvin per grams. If that is in a kilogram, then value will be changed. So it is in a grams. Density of water is around 1 gram per centimeter cube. This is a value that we must know, that density of the water is 1 gram per centimeter cube. If there are 200 centimeter cube of a total solution, which means 200 grams. If the 1 gram per 1 centimeter cube, if there are 200 centimeter cube, then there are 200 grams. So you can imagine this, that if the 1 gram that is equals to 1 centimeter cube per centimeter cube, then for 200 centimeter cube the grams will be 200 grams. So the total mass of the reaction is 200 gram, because 100 centimeter cube of NaOH and 100 centimeter cube of HCl. So total is 200 centimeter cube. That's why 200 gram the mass of the reaction mixture. Rise in temperature is from 28.5 Kelvin to minus 25.0 Kelvin. So it will be 3.5 Kelvin. The change in the delta T, this is a delta T, T2 minus T1. This is a change in temperature. As we know the formula according to glass calorimeter, as we know glass calorimeter is used to calculate the enthalpy of neutralization. So we are going to check the enthalpy when the strong base and strong acids are reacting. The reaction is neutralization. So we are using glass calorimeter formula, that was, here you can see Q, the heat, is equals to mass multiplied by specific heat multiplied by change in temperature. Mass is 200 grams, as the mixture having a total volume 200 centimeter cube, which will be equals to 200 grams, because they will make 200 grams of water. Specific heat of water is 4.2 joule per Kelvin per gram. 3.5 is the temperature change. Reaction is exothermic. When the neutralization reaction takes place, always heat evolves from the system. That's why we have written here reaction is exothermic. So the Q is minus 2.94 kilojoule. That minus sign represent the reaction is exothermic. This value of Q, this value of heat content is not for 1 mole. We have to calculate for 1 mole, and this value is not for 1 mole because our solution is not 1 mole, that is 0.05 mole. How I can say that the solutes are 0.05 mole? Here you can see 100 centimeter cube of 0.5 molar NaOH is equals to 100 centimeter cube of 0.5 molar HCl. 0.5 molar means 100 centimeter cube of solution contains 0.5 moles. As we know the formula of the molarity, moles at the above and in the numerator, that is volume. So 0.5 molar means 1000 centimeter cube of solution has 0.5 moles. Its molarity is 0.5 molar. If there are 100 centimeter cube of 0.5 molar solution, this is for 1000 centimeter cube. These moles for 1000 centimeter cube. But we are given with 100 centimeter cube of each NaOH and HCl. So if there are 100 centimeter cube of 0.5 molar solution, then how many moles of each solute? Then how many moles of each solute? So apply the relation. 1000 centimeter cube of solution has 0.5 moles of solute. 100 centimeter cube of solution having how much? So multiply 0.5 and 100 and divide with 1000. These values will be multiplied and the first value will be in a division. So it will be equals to 0.05 moles of each. So that's why the heat value is per 0.05 moles, not for 1 moles. We have to calculate the enthalpy for 1 moles because as we know the change in enthalpy having a unit kilojoules per mole. So we have to calculate per mole. This is not for per mole. This is for 0.05 moles of each. So let's calculate how we are going to calculate for 1 mole. Here you can see 0.0 moles evolve heat, that is minus 2.94 kilojoules. If there are 1 mole of solute, then minus 2.94 multiply with the 1 and divide with the 0.01 mole. Here you can see the relation. This relation is directly written in your book that you have to divide the heat with the change of the mole, with the molarity. But if you see the relation, you can see here 0.05 mole having a heat evolve, that is minus 2.94 kilojoules. If there are 1 mole of solute, then how many amount of heat will evolve? So minus 2.94 multiply with the 1 and divide with the 0.05. It will be equals to minus 58.8 kilojoules per mole. Next, this sign is just representing the reaction is exothermic. That's why written here minus. This is representing exothermic reaction. Neutralization is an exothermic reaction. Next example is example number 3. See question from your book. 10.16 gram of graphite. Graphite is basically a carbon. Graphite is carbon. So this is the mass for graphite, for carbon. Is burned in a bomb calorimeter. As we know, in a calorimeter, in a bomb calorimeter, we use a combustion reaction. So basically we are combusting the graphite. And the temperature rise recorded. Temperature rise recorded, that is delta T. The change in temperature is given to you, that is 3.87 Kelvin. Calculate the enthalpy of combustion of graphite. You have to calculate the enthalpy for combustion reaction of graphite, for the combustion of graphite. If the heat capacity of the calorimeter, which is basically bomb and water. So we are saying about the heat capacity for bomb and water, that is 86.02 kilojoule per Kelvin. Here you can see all the values written in data. Heat capacity of bomb calorimeter, that is represented as a C, that is 86.02 kilojoule per Kelvin. Rise in temperature, that is 3.87 K, it's delta T. heat gained by the system. How we are going to calculate this? By this formula. As you know, in a bomb calorimeter we use a formula, heat is equals to heat capacity multiplied by change in temperature. So heat capacity is basically the amount of heat required to raise 1 degree or 1 Kelvin temperature. So to raise 1 Kelvin temperature in a bomb calorimeter to water is 86.02 kilojoule per Kelvin. So this is a constant value, known value you have to write here. Change in temperature is given in a question, that is 3.87. Both the values are written. The answer is 332.89 kilojoule. This is not for per mole. This is not for per mole. As we have to calculate delta H for per mole, kilojoule per mole. We are calculating change in enthalpy of a combustion reaction, so we are going to calculate for 1 mole. This is not for 1 mole because graphite is given as 10.16 gram and this is not 1 mole. As we know, 1 mole of graphite will be equals to 12. This is not for 1 mole. So how we are going to calculate that, the moles of these? As we know, the formula for mole is mass over molar mass. Mass of graphite, that is 10.16 and molar mass, that is 12. So by this formula you comes to know this value of heat change is for 0.843 moles, not for 1 moles. So now you have to calculate this for delta H for 1 mole. How you are going to calculate enthalpy of combustion per mole? Simply 0.843 mole having a heat evolved, that is 332.89 kilojoules. As we know, combustion reaction is also exothermic reaction. Heat will evolve. So this is the reaction in which heat evolves. So 0.843 moles evolve heat, that is 332.89 kilojoules. For 1 mole, you have to multiply this value with the 1 and divide with 0.843. So this value will be, the answer will be 395 kilojoule per mole. Now this is for per mole. This value is for 0.843. Now this value is for 1 mole. Write minus sign with this because the reaction is exothermic. The heat is evolved. This is your answer. This minus sign is basically representing the reaction is exothermic or endothermic. If the reaction is endothermic, then plus sign will be written. If the reaction is exothermic, then the minus sign will be written. This minus sign having no use with the calculation. You just have to represent that the reaction is exothermic. Next is Hess's law of constant heat summation. Our next topic is Hess's law of constant heat summation. What is this law? According to this law was given by Germain Hess. According to this law, if a chemical change takes place by several different routes, the overall energy change is the same. If you are doing any chemical reaction in a one step, or if you are doing a same type of forming a same type of product with the same type of reactant but by different pathways, the total heat change, the total enthalpy of that reaction will be same. For example, you are making carbon dioxide. Here, you are forming carbon dioxide. This is a direct equation to make a carbon dioxide gas by carbon plus oxygen, one mole of oxygen There is another way to make carbon dioxide indirectly by two pathways. One pathway is by reacting carbon with half mole of oxygen. First make carbon monoxide, then this carbon monoxide reacts with another half mole of oxygen and make carbon dioxide. So this is a delta H, direct formation of carbon dioxide in a single step, but here you can see by two steps, more than one step. This is a step 1, this is a step 2. First you are making carbon monoxide, then you are making carbon dioxide. So there are two enthalpy changes, delta H1, delta H2. The sum of delta H1 plus delta H2, the sum of these two enthalpy change is basically equals to the enthalpy change that is for single step reaction to form the same product. Clear? According to the statement of Hess's law of constant heat summation, if a chemical change takes place by several different routes, as we seen in carbon dioxide preparation, first carbon monoxide is formed, then carbon dioxide is formed. So there are several different routes. The overall energy change is the same. If you are forming in a single step or if you are forming that carbon dioxide by another route, regardless of the route by which the chemical reaction occurs, provided the initial and the final conditions are the same. Initially the reactants are same, finally the product is same, doesn't matter which type of route you have chosen to form the product. Clear? This is about Hess's law of constant heat summation. Summation means to sum up. So when you are adding all the heats, you will know that is constant if the single step is taken or if many multiple steps are taken. This is the journal pathway. Basically, you can consider this a cycle. A is a reactant. You want to make D from this reactant A. There is some enthalpy change to form A to D. This is a single step. You take single step to make a D, or you take more than one step to make this product D. For example, first you are making A to B. The change in enthalpy is delta H1. Then you are making B to C, any other product rather than D. Change in enthalpy is delta H2. Then you are forming C to D, the enthalpy change will be delta. So there are three heat summations. If you are adding all these three heat summations, that will be equals to delta H. In short, this is considered as a cycle. If you add all these heat summations, it will be equals to 0. If you are adding all these heat changes, all these enthalpy changes, that will be equals to 0. The sum of all the enthalpy change in a cyclic process is always 0. In MCQs, if the question is asked about the sum of enthalpy change in a cyclic process is, so you must know that will be equals to 0, because delta H1, delta H2, delta H3 are equal and equal to delta H. That's why the cyclic process having a value, having a sum 0. This is a sign for summation. This is a sign for summation. Sum of delta H in a cyclic process is equals to, because the change in the enthalpies, if you are doing with a single step or if you are doing with the many different routes to making the same type of product, then the sum of all the enthalpy changes will be equals to 0 according to Hess's law of constant heat summation. basic method we use to calculate the enthalpy change is gas calorimeter and bomb calorimeter, but all the chemical reactions enthalpy you cannot calculate by them. So that for them you use this type of method to calculate. If you are not able to calculate the enthalpy change of D by glass calorimeter or a bomb calorimeter, so how you can calculate the enthalpy change of a D? So you use this method, that first make A to B and check the enthalpy change, then B to C, check the enthalpy change, then C to D, check the enthalpy change. The sum of these all enthalpy changes will be equals to the enthalpy change if you are forming directly A to B. Next example, okay, understand this example with enthalpy change. Carbon plus carbon solid plus oxygen gas reacting and making a carbon dioxide. The enthalpy change is minus 393.7 kilojoules per moles. This is a triangular cyclic path. You are not making directly, you are making carbon dioxide by taking another route first to make carbon monoxide. So delta H1 from carbon monoxide you are going to make carbon dioxide. So carbon monoxide reacts with half of the oxygen to make carbon dioxide. The enthalpy change is minus 298 kilojoule per mole. You have no idea, for example, you have no idea about the enthalpy change, that carbon reacts with half mole of oxygen to make carbon dioxide, then how you can calculate this? As I told you, delta H is equals to delta H1 plus delta H2. If in exams or in a question you are given with two enthalpies and asked by the third one, so you can easily rearrange the equation and calculate this. You know about the delta H, that how carbon and oxygen, 1 mole of oxygen react and make carbon dioxide. You know the change in enthalpy to write its values, and you also know about the delta H2. You have to calculate delta H1. So delta H2 is in a plus, on the other side of equation it will be as minus, delta H minus delta H2, it will be equals to delta H1. Here you can see delta H1 is equals to delta H minus delta H2. So write the value of delta H minus delta H2. In a Hess's law of constant heat summation, this minus sign having an importance. When you are calculating, then use these values. Clear? Minus minus plus, minus plus minus. So you, in Hess's law of heat summation, when you are calculating this negative enthalpy and positive enthalpy having importance, so you have to use these signs in calculations. Next, we having another example, that is sodium carbonate. You are making sodium carbonate in a single step or by two different steps. Sodium carbonate is formed when sodium hydroxide in aqueous form reacts with carbon dioxide, that is in a gaseous form. They react together as 2 and a 1 mole. They will form sodium carbonate plus water. Water in a liquid form. Water in a liquid form. And your sodium carbonate is in a aqueous form. If you are making this sodium carbonate by different pathway, for example, first you are reacting sodium hydroxide with carbon dioxide. First you are forming sodium bicarbonate. By adding H, its name is changed as sodium bicarbonate. Then that sodium bicarbonate reacts with another mole of sodium hydroxide and form sodium carbonate. What is the difference between two reactions? Here you can see the reactants are same, but the products are different. Why? Because the number of moles are changed. In a single step reaction, we are using 2 moles. We are using 2 moles. But in a two steps reaction, you can see here, first we use 1 mole of sodium hydroxide, then another mole of sodium hydroxide is used in a second step. So this is a single step reaction and this is a two-step reaction. The enthalpy change for this single step is minus 89.08 kilojoule per mole. This is the enthalpy change when you are forming directly in a single step. But if you are choosing 2 steps to make this sodium carbonate, the enthalpy change for the first reaction is minus 48.06 kilojoules, and for the second step, enthalpy change is minus 41.02 kilojoule per mole. As I said, if the enthalpy change for a direct reaction is whatever, that will be equals to all the heat changes, all the enthalpy changes when you are forming product by more than 1 roots. Delta H is equals to delta H1 plus delta H2. This delta H is for the direct formation of the product in a single step, and these are the more than 1 steps to form the same product. So delta H, the product is directly formed. Delta H is minus 89.08 kilojoule per mole. When you are forming the same product by 2 steps, so the delta H1 is minus 48.606 plus delta H2 minus 41.02 kilojoules. Plus minus minus, minus minus plus, these both values are added, but the sign is for minus because with the bigger value the sign is minus. You can see here delta H is equals to delta H1 plus delta H2. This is the proof for Hess's law of heat summation, that if you are forming something, the change in enthalpy will be same. Doesn't matter which route you have followed. If a chemical reaction takes place by several routes, the overall change is the same, regardless of the route by which the chemical change occurs, provided the initial and the final conditions are same. Your reactant must be same, your product must be same. Doesn't matter in between you did which changes. Enthalpy change always remains same if you add, if you compare, because this is considered as a cyclic. If you sum up the cyclic reaction, that will be equals to 0. As I told you, we do this Hess's law, we use this Hess's law to calculate the enthalpy change for those reactions those reactions which are not easily calculated by glass calorimeter or bomb calorimeter. So for those type of reaction, we use this Hess's law to calculate. We make the same product by taking different routes and calculating the enthalpy change of the reactions. By adding all those enthalpies, we come to know that the product having same enthalpy change when it is directly formed from its reactant. There are many applications of Hess's law. Hess's law is used for the determination of heat of formation of compounds such as carbon tetrachloride. As we know, heat of formation of compound, the compound is formed from its own elements. That is called as enthalpy of formation or heat of formation of compound. There are some compounds like aluminum oxide, boron oxide. We cannot calculate their heat of formation directly because it is very difficult to calculate their heat of formation. So for their heat of calculation for their heat of enthalpy, we use this method, Hess's law of heat summation, like aluminum oxide, boron oxide. Because their oxides make a protective layer, that's why we face a difficulty to calculate their enthalpy change in bomb calorimeter and in glass calorimeter. If you want to calculate heat of formation of carbon monoxide, then it is also very difficult to calculate from glass calorimeter and from bomb calorimeter. So for the calculation of heat of formation of carbon dioxide from carbon monoxide, you use Hess's law of heat summation. Hess's law of heat summation having a very important application, that is Born-Haber cycle. This is our next topic, Born-Haber cycle. This cycle or this process we will discuss on Monday.